Hello, it is Cold Bucket. Today is March 15th, 2026, and this is my third entry documenting my progress in learning cybersecurity. In my last video, I was going over OSI mainly and the different layers in that. I'm gonna hit back on that again today because I need to submit that down, I think. So, I'm probably gonna have to do studying outside of this too. I don't know what I'm gonna do. I'll probably be like I don't know. I don't know how to learn this more than just reading it over and over again. I can't even do this in a book yet. These are too long. But, okay. So, today I spent a lot of my time on Try Hack Me again. I feel like it's a pretty nice tool that I'm using. I don't know how well it's preparing me, but I feel like I'm learning lots of verbiage and just like terms and stuff. I guess it would be helpful to be technical in this field, considering it's all technical. I've been awake for a while, if you couldn't tell. And so after that, I downloaded a Python and started to learn some of the basics on there. I feel like I learned a lot in just one night, even though I'm still pretty bad at it. I'm planning to keep I want to get a lot of these like terms and stuff down from Try Hack Me first, but I'm gonna be trying to learn some Python on the side too. So yeah, I think that's going to be very, very important. So then later in the night, I went back to studying some concepts. I guess when I started this, I spent a lot of time talking about the OSI model, and I'm gonna spend a lot of time talking about it again. I'll try to go faster this time though. Alright. Layer 1, physical. This is the easiest one. This is just going to be your hardware. Cables, devices, routers, switches, stuff like that. Easy peasy, lemon squeezy. Alright, then we got data link. Okay. Yep, this is where I'm just going to have to read my notes again. Physical addressing of transmission. It receives a packet from the network layer, including the IP address for the computer, and adds in the physical MAC address of the receiving endpoint. Okay. Inside every network-enabled computer is an NIC network interface card, which comes with a unique MAC address to identify it. So, I guess the NIC is the hardware part of it, and I guess the MAC is the number associated with that, if that makes any sense. It's the job of the data link to present data in a format suitable for transmission. Okay. Network. So this is going to be like routing and reassembling data. So it's going to take your small chunks, your packets, and it's going to form that into one big chunk. So it's also need to figure out the most optimal path to send your data to. And let's see. Let's look here at my notes. Determines the most optimal path in which these chunks of data should be sent, while some protocols at this layer determine exactly what is the most optimal path the data should be sent to another device. These protocols include open, shortest, fastest path? Dang it. Open, shortest path first, and routing information protocol. Okay. So, look at that. That's going to be what is the shortest route there? How can I get this data there in the shortest path possible? Okay. Then, what is the most reliable path? Has a path ever lost packets on it before? Third, what is the fastest path? What path gets my data there the fastest? And yep. Okay, next we got transport. Okay, so this is your TCP and your UDP. Let me get some water. Alright, TCP, Transmission Control Protocol. This is your reliable, your secure one. This is going to be making sure that every packet from your source address is going to arrive to your destination address. Okay. If one small, tiny little packet doesn't arrive, the entire chunk is gone. Let's see. The thing about this is, though, resource heavy. It's gonna use a lot of resources. It's slower than a UDP. You're gonna use this for like downloads, probably like YouTube videos, images, stuff like that. Alright, UDP, User Datagram Protocol. So, let me hit back. So, TCP is a way connection handshake. Between what? I don't know. I would assume it's between device 1, maybe server. No, I don't know. Device 1, device 2, port. I don't know. So let's see. And this is a connection. This is a connection-based one. You have to have a connection there. All right, UDP, User Datagram Protocol. This is a connectionless protocol. So we don't need a connection for UDP to be established. So this is going to be your fast one. It's just going to be sending data out as fast as it can, when it can. It doesn't care if it loses data or not. And when you lose data, that's packet loss. So this is going to prioritize like your real-time communication, like your audio and videos, live streaming, video calls, audio calls, something like that, conferences, broadcasts, stuff like that. So let's see, advantages of TCP: guarantees the accuracy of data, capable of synchronizing devices to prevent each other from being flooded with data, performs more processes for reliability. Disadvantages: if one small chunk is lost, the entire chunk of data cannot be used. TCP is slower than UDP. Alright, 5, session. When a connection is formed, a session also has to be formed with that connection. The session is also responsible for closing the connection once it's been open for too long, if there's no data coming through, or reasons like that. Something about bandwidth, I think. Taking up bandwidth and resources, having that connection open is taking resources, and a session is in control of that. And so you're going to also have security checkpoints here too, I think. Okay, let's see. Let's read my notes. Session: once data has been correctly translated or formatted from the presentation. Layer 6, yeah. The session layer will begin to create and maintain the connection to the other computer for which the data is destined. When a connection is established, a session is created. Whilst the connection is active, so is the session. The session layer is also responsible for closing the connection if it hasn't been used in a while or if it is lost. Additionally, a session can contain checkpoints where if the data is lost, only the newest pieces of the data are required to be sent, saving bandwidth. Sessions are unique, meaning data cannot travel over different sessions, but only across. So maybe there's no security checkpoints. That might be done in the presentation. So presentation, this is going to be formatting it all to. It's going to act as your translator, really. You're using an email client, and the person you're emailing is using a different email client. It goes through this presentation layer. It's all going to come out the same. Let's see. Yeah. Because software developers can develop any software such as an email differently, the data still needs to be handled the same. This layer acts as a translator for data to and from the application layer. The receiving computer will also understand data sent to a computer in one format destined for another format. For example, when you send an email, the other user may use another email client, but the data still displays the same security features. Okay, yeah, so yeah. Such as data encryption like HTTPS. Let's see. Hypertext. Transmission protocols. Secure. When visiting a secure site, occur at this layer. Alright, then we get application. This is just GUIs, really. You're on the GUI watching this video. If you're watching this, future me might be watching this. Let's see. So this is how the user should interact with data sent or received. Everyday applications such as email clients, browsers, or file server browsing software such as FileZilla provide a friendly GUI graphical user interface. I'm sure everybody knows that. For users to interact with data sent or received, other protocols include DNS, domain name service system, which is how website addresses are translated into IP addresses. Alrighty. I'll skip over that. Just talk about packets and frames. Frames like envelope. Packets is. Oh, we got some headers here. Time to live. That's easy. Expiration date on it, or an expiry time on it. So this is just going to save resources. It has to close at some point. This field sets an expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. Checksum. So checksum, this is going to, it's going to estimate how much is going to be received or sent. Maybe that's and or, not sure. And if it doesn't come up to that estimation, then its checksum is off and that data is corrupt. Source address. This is just where the data is coming from. The IP address where it's coming from, so that the data knows where to return to if need be. Destination address, this is just where the data is going. This is so the data knows where to go. Let's see. Oh, packets that go through TCP contain various sections of information known as headers that are added from encapsulation. So that's just adding stuff on top of packets. So source port, this is going to be, well, your source port. This is where it's going to be coming from. Let's see. The port opened by the sender to send the TCP packet from. Okay. The value is chosen at random out of ports from 0 to 65,535 that aren't already in use at the time. Destination port, this is just the port that it is going to. But this will be running on port 80 normally. This value is not chosen at random. Source IP, need I explain? This is just this is the IP of the device sending the packets. Destination IP, same thing pretty much. This is just the destination. This is just the destination of where the packets are going. Sequence number. Okay, I do not know this one. When a connection occurs, the first piece of data transmitted is giving a random number. Oh, okay, here we go. Acknowledgement number. After a piece of data has been given a sequence number, the number for the next piece of data will have the sequence number plus 1. Checksum, already went over that. Data, data as a flag. The header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors. Oh, looks like I went from blue pen to black pen. Okay. So the three-way handshake used by TCP has a few special messages. Send. So this is the initial packet sent by a client during the handshake. So device 1 is going to. Well, hold on. I'll get to that in a second. This packet is used to initiate a connection and synchronize the two devices together. Then you have your send acknowledgement, send ack. This is going to come back to that first device. The packet is sent by the receiving device server to acknowledge the synchronization attempt from the client. Then you have acknowledgement. The acknowledgement packet can be used by either the client or the server to acknowledge that a series of messages/packets have been successfully received. Data. Once a connection has been established, data such as bytes of a file is sent via the data message. Fin. It's just finished. That's just saying that they're done sending data or they're done receiving data. RST. This is just to shut the crap down. If for some reason you need to shut it down quickly. TCP will close the connection once a device determines all data has been received. Since TCP reserves systems resources on the device, it is best practice to close the TCP connections ASAP. To initiate the closure of a TCP connection, the device will send a FIN packet to the other device. And that other device will have to acknowledge this finished packet. So device 1 is going to send, with send and send acknowledgement, device 1 will send to device 2. Device 2 is going to send acknowledgement to device 1, and then I feel like that should be acknowledged. Okay, but it's just going to send back. And then with closure, this is going to be device 1 is going to send a finish packet to device 2. Device 2 is going to acknowledge that finish and then send another finish packet of their own, and then device 1 will acknowledge that finish packet. In the background here, this is my Linux. Shoot, not Linux, Python. Too lazy to cut that out. And I'm lazy as hell. Okay, UDP is a stateless protocol. Yep. Remember that. UDP also has headers. UDP packets are much simpler than TCP packets and have fewer headers. However, both protocols share some standard headers, which are these: time to live, source address, destination address, source port, destination port, and data. So this is a pretty simple one. Device 2 is just going to request data from device 1, or vice versa. And device 1 is just going to send lots of responses out at once, lots of data out at once. Here we go, ports. So ports are pretty essential in how data is exchanged. Because ports can range anywhere between 0 to 65,535, there quickly runs the risk of losing track of what application is using what port. So applications, software, and behaviors are associated with a set of standard rules. For example, by enforcing that any web browser data is sent over port 80, software developers can design a web browser such as Google, Chrome, or Firefox to interpret data the same way as one another. So this means that all web browsers are sharing a common rule. Data is sent over port 80. How browsers look, feel, and how easy they are to use is up to the designer or user's choice. Let's see. While the standard rule for web data is port 80, a few other protocols have been allocated a standard rule. Any port that is within 0 and 1024 is known as a common port. Okay, then here we go. We have these ports. FTP, File Transfer Protocol. This is port 21. This is just going to be a file sharing application built on a client-server model. You can download files from a central location. Then we have Secure Shell, SSH. This is going to be, hold on, no looker. Port 23. Damn it. Port 22. This protocol is used to securely log into systems via a text-based interface for management. We have HTTP. I'm sure we've all seen that. Hypertext Transfer Protocol. I think I said transmission earlier. This has been in port 80. Just cheated. I looked at it. This protocol powers the World Wide Web. www. Your browser uses this to download text, images, and videos of web pages. Then we have server message block, SMB. This is on port 445. This protocol is similar to FTP, however, as well as files, SMB allows you to share devices like printers. So I guess you're using that when you're printing something. HTTPS, this is a hypertext transfer protocol secure. This is on port 443. Let's see. This protocol is the exact same as HTTP, but securely using encryption. Then you have RDP, Remote Desk Protocol. This is on port 3389. This protocol is a secure means of logging into a system using a visual desktop interface. And this is as opposed to the limitations of the SSH protocol. Okay, let's see. Oh, port forwarding. Here we go. Port forwarding is an essential component in connecting applications and services to the internet. So if you're not port forwarding, applications and services, such as web servers, are available only on devices on the same direct network as those, and that's called an intranet. So only the devices on this network communicate with each other. They can't communicate with the public internet. So yes, if a website was to be accessible to the public using the internet, they would have to implement port forwarding. Port forwarding is configured at the router of a network. Alright, then we hit on firewalls. So a firewall, I'm not even explaining that. Everybody knows what a firewall is. So your firewall is going to ask a few questions though, as to the data that it's receiving or sending. So it's going to ask, like, where is the traffic coming from? Where is this data coming from? Is your firewall configured to accept or deny data coming from a specific network? Where is this traffic going to? Same thing, has your firewall been configured to accept or deny traffic destined for a specific network? What is the port of this traffic for? Has the firewall been told to accept or deny traffic destined for ports for a specific port only, such as port 80? What protocol is the traffic using? So is it using UDP, TCP, or both? Is your firewall configured to accept one of those? Firewalls perform packet inspection to determine answers to these. So firewalls can be configured in a lot of ways. So these can be dedicated pieces of hardware. You're going to find these a lot more often in large buildings or companies. And then you can have residential router firewalls, and then you can have software firewalls. And firewalls have a few different categories too. I only learned 2 so far. I've learned of stateful firewalls. This is going to be a... So this is the way I understand it, is that this firewall is checking all of the data. It's checking all the data coming through it at once. Or not at once, but it's checking all of it. So the firewall determines the behavior of a device that's sending it, or it could be sent to, based upon the entire connection instead of just in an individual packet. The thing about this firewall is that although it is very secure, it's very resource heavy in comparison to the stateless firewall. Its decision making is dynamic. So, for example, a firewall could allow the first parts of a TCP handshake that would later fail. And if a connection from a host is bad, it will block the entire device. Alright, then we have stateless. This firewall has a static set of rules to determine whether or not the individual packets that it's scanning are acceptable or not. So, if a device is sending a bad packet, that will not necessarily mean the entire device is going to be blocked. While stateless uses far fewer resources than the other categories, these are much dumber. These firewalls are only effective as the rules that are defined within them. If a rule is not exactly matched, it is effectively useless. Yes, that is verbatim from TryHappy. However, these firewalls are great when receiving large amounts of traffic from a set of hosts, such as a distributed denial of service attack, a DDoS. And that's all I've studied so far for today, or not today, for this log. I hit on the I want to call it Linux, Python again. All I really did on that was needed some water. I just watched like an hour tutorial. I was just trying to learn some basic, like, I guess just like the basics of Python. I learned strings, integers, floats, inputs, prints, module. I learned of modules, not the modules. I know there's a random module. Let's see. I made operators. I learned how to convert like strings to different I guess values. I learned variables. And with that, I was able to obviously, well, no, because I guess I did make that without watching the video. Well, in the video that I watched, we were tasked with making a project, and then we would later see how they would make it, how they made it in the video. The first one I got was, it was a weight converter. You put your weight in, and then if you put in kg, it'd convert it from kg to lbs, vice versa. I had some issue near the end of it, I think, and I had to go on and see how they did it. It was something with the operators and how I don't think I was able to get a float to a string. But, and then I also made a very short calculator too. And, I think I actually expanded on that calculator further than I was expected to in that video. In the video, I think we were just tasked with making a simple addition calculator. I pushed myself the extra limit, and I tried to see if I can get myself to do, if it could come up with different operators too, like division, multiplication, and subtraction. And I was actually able to do that. I felt pretty proud of myself. I guess Python did help me in that aspect, though. I got ChatGPT to help me with a number guessing game. That's how I learned of the random module and how I learned of modules. I learned loops too. I'm not great at them. I can break them. The continuing though, it kind of just loops. Even I don't know, but that's actually about it, I think. Let's see here. Yeah, pretty much it. Well, I've talked for about 30 minutes. 30 minutes longer than I normally would. And I guess that's it. If anybody has suggestions for what I should focus on or tools I should be learning, I'll take that too. Ciao.